In this video, I'll talk about URDF in ROS 2. The basic stuff which I would cover in this video are about links and joins, and also how to use STL files for the URDF. So what is URDF? URDF is Unified Robotic Description File. So any robotic application which you see on the screen, which is being simulated, needs a URDF file, because that is the one which represents what are the links and what are the joins. And if you want to build your own robot, learning URDF is the first step towards that goal. So what makes up URDF? Basically two things. One is the link, and another one is the joint. So if you take a robot, it's connected using links. It consists of links, and these links are connected together using joints. And one thing which is common in both of these things, either the links or the joints, they have a coordinate system which represents them. So in order to dive deep into the URDF file, we need to understand the coordinate system much better and the conventions which are involved along with that. So if you see here, the coordinate system has, there is an easy way to remember this, as in RGB, the colors represent each of the axes, the XYZ axis. So in the order of RGB is you can relate it to XYZ. So if you take red represents the x-axis. If you take green represents the y-axis. And if you take blue, it represents the z-axis. And similarly, the rotation coordinates for this is the roll, pitch, and yaw. And they too follow the order of R, P, Y, and you can relate everything in this order. So if you see a red axis, it means an x-axis. And if you take roll, it's a rotation about the x-axis. And if you take pitch, it's a rotation about the y-axis. And similarly, the yaw. Once you have understood this fundamental thing, defining your own links and joins becomes much more easier. And in terms of the joins, there are different types of joins. And some of the main things which you can often see in different URDF files is revolute joint and the prismatic joint. The revolute joint describes how much a link can rotate with constraints on the lower bounds and the upper bounds. The one which you can see on the top right is the revolute joint. And for the prismatic joint, you can see on the bottom right is the prismatic joint, where it's basically the motion of going forward and backward about an axis. And the two other important ones are the continuous, which is mostly used for defining a wheel, which doesn't have an upper and lower bound, and the fixed axis to define the world coordinate or anything which is just fixed and it doesn't rotate about the other links. The other two, floating and planar. Floating is used for cases when it's not constrained, and planar is used when it's constrained on a plane. So let's dive deep into a URDF file, which was written to simulate a simple robot, which just has two links in it. So if you see here, the URDF file consists of different tags. The first one represents what is the XML version, because all the URDFs are written in the XML version. And one good thing is that in ROS 1 to ROS 2, there has been no changes with respect to this XML format or the URDF itself. So if you can see here, it starts with the robot tag, and this tag defines that whatever defined inside belongs to this robot called origins. And then you can see here, there are tags for links and the tags for joins. Let's talk about links first. So the links consist of visual tag, and it also consists of inertial and collision, which I will not talk about in this video. But in terms of the visual tag, it's the tag which defines what we are going to display on the visualization software. For example, here, the links, what we want to be displayed are just cylinders. So how we do that is that we include a geometry tag inside that and define a cylinder with the length requirement and the radius requirement. So that's the same thing defined for the link 1 as well. And another thing which is not defined over here, but defined below, is the origin tag, which defines where the local coordinate of that link is with respect to the joint it is defined to. Let me go a little bit more clearer here. This is where the joint comes into the picture. So if you see here, the base link does not have joint predefined in this URDF, but it is the first link, and it's always the fixed link, and that's where the joint is also represented. And that's why we do not have the origin defined for the base link, because when we don't define it, it sets the roll, pitch, yaw and the XYZ as 0, 0, 0 for both of them. And that's why we don't have the RPY and XYZ, because in this case, the joints coordinate axis and the links coordinate axis are on the same point. But if you take the second joint, which is here, which is basically the base link to link one, this joint is very important. And you can see that this link is defined with respect to the previous link, a previous joint, and the coordinate system, like how it's been translated and rotated, is given here. It says that you need to translate 0.05 in the z-axis, and there is no rotation. So that's why the joint is over here. For the second joint, for this link one, we define the link one with respect to the joint which it's connected to. So if you see here, the joint has several tags. The first two tags represent which is the parent link and which is this child link. The parent link being here the base link, and the child link being here the link one. And another thing, which another two tags which you can see here are the axis. This defines the axis of rotation, and over here it's defined as the z-axis. And the last one is the limit tag, which defines the bounds on how much it can rotate, as it's a revolute joint. Here we have defined it as minus pi by 4, pi by 2 to plus pi. And in terms of the effort and velocity, we have defined it as 302, just to make sure that it's rotating, but we will not get deep into the details over here. And because this link one is defined with respect to the parent link, which is the base link, so this link one will be defined from the joint's coordinate axis. So if you take the link one, you can see that the link one's coordinate axis is pushed by 0.25 in the z direction from where the joint base link to link one is defined. So that's how it's all connected, as in the links and the joints and everything. Take the links and the joints both have coordinate axis, and how you position them is how you will expect the final rendering to be. So if anything goes wrong in this, the final rendering will not be as you wanted. And just another example here, if you this is to describe how we are going to place this orange link with respect to the link one here. So you can see here that first we define the joint where we are going to connect the link one and link two to. So the joint is defined with respect to the previous joint, which is joint one here. And you can see here that it is being, in order to define this joint two at this particular place and orientation, we need to translate it by 0.5 in the z direction and minus 0.15 in the x direction. So that's how this coordinate frame is located here. And then you can also see there is an orientation change. That is, the z direction is towards the right side. And this can be done by rotating it by minus pi by 2. And that's how you get this coordinate frame for this joint 2 at this location. This rotation is done so that we follow a basic convention that always the z-axis is the axis about which it rotates. And in order to define the link 2, which is a child, if in this joint, the child with respect to the joint 2, we define this the coordinates axis of the link 2 from this coordinate axis. So how do we define it? We have to so we have to translate this coordinate axis 0.3 in the x direction and 0.1 in the z direction. And then we need to rotate this back by pi by 2. And that's how we get the coordinate axis, which is as shown here, where the z axis is pointing on top and the x axis is pointing on the left-hand side. So this is how the translation and the rotation takes place. Always remember that first we do the translation and then we do the rotation, so that so first we do the translation and then we do the rotation, so that we get we stick to the common nomenclature, common convention. And this whole this image was taken from Aleksandar Haber's tutorial, which was an inspiration for me to do this and share the learnings from. And then another type which I wanted to share was the prismatic joint, in this case, the grippers, as you can see here. And for here to define this prismatic joint, it's similar to all the other joints which we discussed before. We set a parent link, and then we set a child link. And here, what you can see, which is different, is that we set the axis as the x-axis, which is the red color here. And because this is the axis which is defined for the prismatic joint, this is where about which it will move front and back. And here the lower and upper limit represents that what are the bounds for this front and back motion, which is allowed for this particular link. Remaining all the other things remain the same. Just that in order to define a prismatic joint, we need to define the axis accordingly. So once all of this is done, this is the output which we get if we go step by step for each of the links, and we would be able to visualize the whole robot. Another common thing which arises in this creating URDF is that we want to add STL files to a defined location. Say we need to add a custom gripper here. This is a case where we want to add the custom gripper to the end of this cylindrical pole here. So you cannot use the primitives such as like cylinder box to create it, but how you can go about doing this is by using the mesh where we create this shape. And then the only thing which changes here is that inside the geometry tag, we include mesh as another tag, and we define the file name, basically the location where this mesh file is located. And in order to locate this, it remains the same as for the cylinder, which we discussed before, is that there is a local coordinate system for that particular mesh file. What we have to do is that we need to set this local coordinate system at the appropriate position with respect to the joint it's defined to. So it's the same concept. What we need to do is we need to understand where exactly the local coordinate system is for the mesh, and then we would be able to locate it perfectly at the desired location. This winds up my entire discussion on the URDF files. So going through these small snippets would give you an idea of like how do we go about defining each of these links and joins so that we can visualize the robot which we want to control using move it or any other things down the line. So hopefully this was useful and you can use it in the URDF you are building it next. Thanks a lot and have a nice day.